Welcome to G Fun Facts Online. Today we're diving headfirst into one of the most mind-bending questions of our time. Are we living in a computer simulation? This isn't just a late-night dorm room debate or a plot from a sci-fi movie anymore. Philosophers, physicists, and tech billionaires are taking this idea seriously, sparking a quest to find out if our reality is the real deal, or just a very advanced piece of software. So, is our universe a digital cosmos? Let's look for the glitches in the matrix. The idea that our world is an illusion isn't new. It's a thought that is echoed through history. In ancient Greece, Plato imagined us as prisoners in a cave, mistaking shadows on a wall for the real world. In ancient China, the philosopher Zhuangzi famously dreamt he was a butterfly, and upon waking, couldn't be sure if he was a man who had dreamt of being a butterfly, or a butterfly now dreaming he is a man. This captures the slippery nature of our own consciousness. And in Hindu philosophy, the concept of Maya describes our perceived world as an illusion masking a deeper divine reality. But it was the 17th century philosopher René Descartes who formalized this skepticism. He imagined an evil demon powerful enough to create a complete illusion of an external world, tricking all his senses. While Descartes famously concluded, "I think, therefore I am," his thought experiment set the stage for the modern simulation hypothesis. The person who truly brought this idea into the 21st century is philosopher Nick Bostrom. In a landmark 2003 paper, he didn't argue that we are in a simulation, but that one of three very startling possibilities is almost certainly true. This is Bostrom's trilemma. Proposition 1, the extinction proposition. This says that almost all civilizations at our level of development go extinct before they can develop the technology to run high-fidelity ancestor simulations. Maybe we blow ourselves up, or a natural disaster gets us. In this case, no simulations are ever made. Proposition 2, the disinterest proposition. This suggests that advanced, or post-human, civilizations could run these simulations, but they simply choose not to. Maybe they find it unethical, boring, or they have other priorities we can't even imagine. Again, if this is true, we are almost certainly not in a simulation. Proposition 3, the simulation proposition. If the first two propositions are false, meaning that civilizations regularly survive to a post-human stage, and they are interested in running ancestor simulations, then the number of simulated realities they create would be astronomical. The number of simulated conscious minds, like ours, would vastly outnumber the real biological minds. Therefore, for any randomly selected conscious being, like you, the statistical probability of being in a simulation is overwhelmingly high, close to 1. Bostrom's logic is powerful, but it rests on a key assumption called substrate independence, the idea that consciousness isn't tied to our specific squishy carbon-based brains, but can run on any sufficiently complex computational system, like a silicon-based computer. Inspired by this philosophical argument, scientists started to wonder, could we find empirical evidence? Could we find a crack in the code? One of the most compelling ideas comes from physicist Silas Bean. He and his colleagues proposed that if our universe is a simulation, then space-time itself might not be smooth and continuous, but discrete, like pixels on a screen. This underlying grid or lattice structure would impose tiny limitations on the physics of our universe. Specifically, it would affect the behavior of particles at extremely high energies. They suggested looking at the spectrum of high-energy cosmic rays. These are the fastest, most energetic particles we've ever observed. In a continuous, smooth space-time, they should arrive on Earth from all directions more or less equally. But if space-time is a discrete grid, the math suggests there would be preferred directions, creating a non-uniform pattern. They also predicted a sharp cutoff in the energy spectrum of these cosmic rays. So far, we haven't observed this signature. The main problem is that the highest energy cosmic rays are incredibly rare, making it extremely difficult to gather enough data to spot such a subtle pattern. Another, more controversial line of inquiry comes from physicist Melvin Vopson. He proposes that information isn't just an abstract concept, it's a fifth state of matter, alongside solids, liquids, gases, and plasmas, and that it has mass. From this, he formulated what he calls the second law of infodynamics. We all know the second law of thermodynamics, which states that entropy, or disorder, in a system tends to increase over time. Vopson's law suggests the opposite for information. He claims that information entropy in a system tends to decrease or stay constant. Why is this relevant? Because in a simulated universe, computational resources would be finite. A program that automatically compresses data and minimizes information would be incredibly efficient. Vopson claims to see this principle at work in everything from genetic mutations in viruses to the arrangement of electrons in atoms, arguing they all trend towards a state of minimal information. However, the wider scientific community is deeply skeptical. Critics argue his law is not a fundamental principle of physics, but an observation of specific systems, and that his definition of information is too loose. It's a thought-provoking idea, but it's far from accepted science. While scientists search for glitches, others point to massive hurdles that make the simulation hypothesis seem almost impossible. Let's start with the computational power required. The observable universe contains an estimated 10 to the power of 80 particles. To simulate our reality with any accuracy, a computer would have to track the state, position, and interaction of every single one of them all at once. Physicist Michio Kaku points out that even simulating something as simple as the weather on Earth is beyond our most powerful supercomputers. He says the smallest thing that can simulate the weather is the weather itself. This leads to a logical paradox. A computer capable of simulating our entire universe would have to be more complex and contain more information than the universe itself. If the simulators exist in a universe with the same laws of physics as ours, this seems like a flat-out impossibility. Then there's the energy problem. According to physicist Franco Vazza, every computational operation has an energy cost. He calculated that simulating the entire visible universe down to the smallest possible unit of space, the Planck scale, would require more energy than exists in our observable universe. The numbers are staggering. Just to initialize a simulation of our Milky Way galaxy would require an unimaginable amount of energy. To run it continuously would be a colossal energy drain. These computational and energy requirements are perhaps the strongest scientific arguments against the idea that we're living in a simulation run by a civilization within a universe similar to our own. But what if the clues are right in front of us, hidden in the very fabric of reality? The strange world of quantum mechanics has become a fertile ground for simulation theorists. Take the observer effect, famously demonstrated in the double-slit experiment. When you're not looking, a particle like an electron acts like a wave, passing through two slits at once and creating an interference pattern. But the moment you place a detector to see which slit it goes through, the wave behavior collapses, and it acts like a solid particle. Simulation proponents say this is exactly how a video game works. To save processing power, a game only renders the details that are in the player's line of sight. Everything else is left in a state of lower detail or simple probability. Perhaps our universe only renders the definite properties of a particle when a conscious observation is made. Then there's quantum entanglement, which Einstein called spooky action at a distance. When two particles are entangled, their properties are linked, no matter how far apart they are. If you measure one, you instantly know the state of the other, faster than light could travel between them. From a simulation perspective, this isn't so spooky. The two particles could simply be linked variables in the underlying code. The connection exists outside the simulated spacetime, so there's no violation of the speed of light. Of course, these are just interpretations. Physicists have many other explanations for quantum weirdness, like the Copenhagen and many worlds interpretations, that don't require a cosmic computer. In fact, physicist Sabine Hassenfelder calls the simulation hypothesis pseudoscience. arguing that it isn't a real scientific theory because it simply replaces one mystery, why is quantum mechanics so strange, with another, who are the simulators? It doesn't offer any truly testable predictions. This brings us to the ultimate question: consciousness. If we are in a simulation, is our sense of self, our subjective experience, real? Bostrom's argument assumes simulated beings can be conscious. But what if they can't? What if they are just philosophical zombies, complex programs that look and act human, but have no inner experience, no lights on inside? If that's the case, we couldn't be simulated, because we know we are conscious. Philosopher David Chalmers offers a different take. He argues that even if we are in a simulation, our lives and experiences are still perfectly real and meaningful. A simulated world, he says, is a real world, just one made of information instead of traditional matter and energy. So where does this leave us? Is our universe a simulation? The honest answer is we don't know, and we may never be able to prove it one way or the other. Any glitch we find could just be a feature of the simulation. The arguments against it, based on the sheer computational and energy cost, are incredibly strong. They suggest it would be physically impossible to run a simulation of our universe from within a similar universe. Ultimately, the simulation hypothesis serves its greatest purpose as a philosophical tool. It forces us to question our most basic assumptions about reality, consciousness, and our place in the cosmos. Whether our existence is a product of random physical laws, a divine plan, or a line of code, the quest to understand it is what drives science forward. And who knows, maybe one day, we will find that definitive proof, that irrefutable glitch in the Matrix. Until then, the question will continue to linger, a tantalizing whisper in the cosmic wind.